round for the day. There's a reception right after this session at 4:30. Just out, I believe, my guess is that it's just going to be literally behind this wall. I hope you will be able to join. And then with that, over to you, Spencer, for the last round. Thanks.
Okay. At the end of the last session, we had introduced the augmented graph construction, which is used to reason about, which is a device for proving rules in the do calculus, because we can manipulate additional independencies involving these intervention variables correspond to statements about when you can ignore observations or actions or switch between observations or actions. Yes?
Sorry, one question. As a reminder, what graph is the GXZ? Yeah, over the X.
Yeah, so the question is, what is this graph here? G with an X bar over and a Z bar under it. So I get to define Z bar under it. So the answer is X bar is you remove all the edges from parents of X into X. Z bar is you remove all the edges from children of Z, from Z to children of Z. And yeah, so the next thing we're going to do is prove rule 2, which tells us when we can replace an action with an observation. Yes?
I'm sort of losing the bigger picture. Why do we want to do these transformations, or what's the purpose of?
The purpose is, well, we're going to state and not show, but state that, and I can direct you to the paper in which it's shown, that these rules are sufficient for determining identifiability of interventional distributions from observable distributions.
Okay.
So if it's possible to identify an interventional distribution, then you can do it by applying these rules in some order. It won't necessarily be easy to do it, and I wouldn't recommend trying to do it necessarily by hand if you have a complicated example, but it can be done. And these are sort of the fundamental building blocks of manipulating and interventional distributions, in particular, you're eliminating things you don't want and getting them into a nicer form. Yeah, okay. So let me tell you the statement of, well, before we prove rule 2, which will turn out to be easy to prove, once we have this lemma, we're going to prove this lemma. And so what does this say? This relates deseparation in the original graph, sort of the original graph, that is the graph where we've intervened on X and removed all the edges into X, and where we've removed edges out of Z. And you'll see why that's relevant later, but we're going to relate deseparations in this graph H to deseparations in the augmented graph with respect to H, or with respect to Z, where we're now looking at deseparations between this intervention variable for Z and Y, right? And so you can see, hopefully, why this deseparation might be useful, right? Saying that Y is deseparated from this intervention variable for Z, given X, Z, and W, is exactly what you'd think it is. It's saying that once I've observed X, Z, and W, telling me whether or not Z was obtained via an intervention doesn't give me additional information about Y. And so that's exactly what this statement says here, right? Once I've conditioned on, or once I've, it's almost what this statement says, right? Once it's saying that I can switch between doing Z and observing Z without any change in the resulting distribution on Y. So our first task is to prove this lemma, which is not too bad. So how do we go about doing this? So we are going to prove each direction separately, and we're going to do the same sort of reasoning that we've done before, which is take active trails in witnessing deconnection here, turn them into active trails witnessing deconnection here, and vice versa. So let's say we have an active trail T in H between some X star, some Y star, given X and W. And we now want to find an active trail in this augmented graph between Z hat and Y. So, sorry, this should be Z star. So by Z star, I just mean some arbitrary element of Z. Okay, so the first thing to observe is this active trail can't pass through any Z vertices because, right, we're working in this graph H where we've removed all the edges out of Z vertices. And so the only way to pass through any of the other Z vertices is to use it as a collider. But we're not conditioning on Z here. So this would deactivate the trail and it has no descendants that we could be conditioning on to make this part active. So it would immediately deactivate the trail. So this can't happen. So the only Z vertex that can appear in this trail is Z star, which means that we can modify the trail by just adding to it the edge from Z star hat to Z star. And now we know that the subsequent edge that occurs in the trail T must have been an edge into Z star because, again, there are no edges out of Z star in this graph H. So the trail starts off, so our new modified trail is going to start off with a collider that looks like this. And we are interested in a conditional independent statement with respect to where we're conditioning on Z in this augmented graph. So this collider is in fact active when we condition on Z. And since there are no other occurrences of Z vertices elsewhere in this trail, we immediately get that everywhere else in the trail remains active since we're not conditioning on anything in the trail. And we're not removing edges when we go to this augmented graph. So we immediately conclude that this trail where we've just added this one edge is active in the augmented graph. Okay. So deconnection in H implies deconnection here. Now we need to do the other direction. Okay, so for the other direction, we're going to let T be an active trail in this augmented graph. Between Z hat star and Y star, and we're now going to add to our conditioning set Z. Okay, so let's look at what the start of this trail looks like. It's going to have an edge from Z hat star to Z star, because that's the only edge incident to Z hat star. And it ends at some Y star. And first observation is, well, so another observation is not only does this have to be the first edge, but the next edge has to be in this direction because, again, there are no edges leaving Z star. So we start off with this collider that is made active by conditioning on Z star. So now I want to consider the collider on this trail nearest to y star that contains a descendant in the conditioning set that is reachable, that has a directed path to a descendant in Z that doesn't pass through an X or W vertex. So that's a mouthful. So what I want to consider is the collider on this trail nearest to y star, satisfying the additional criterion that it has a descendant in Z that doesn't get reached by going through an X or W vertex. So why must any such colliders exist? Because this right here is an example of one. There may not be any others. This may be the only one, but this is a collider where the collider contains a descendant in Z, namely the vertex itself, that is reachable without going through any X or W vertices because it has a path of length 0. So let's find the one closest to y star. And now let Z of j, or Z sub j, be the vertex in Z that is reachable via the path I described from C. And now we're going to look at a new trail that we get by concatenating this part of, or this path here to this trail here. Okay, so first observation is there are no Z hat vertices along this trail because Z hat vertices have degree 1 and everything along here has degree 2. Or at least degree 2. Moreover, and so since Z hat is the only place where H differs from this augmented graph, we know that all these edges exist in the non-augmented, or sorry, in H without the augmentations. Moreover, there are no other Z vertices along this trail than Zj, because if they were, they would have to be in colliders because there are no edges going out of Z vertices in this graph. And we've already picked this to be the furthest right collider that has a Z vertex as a descendant. And if there were any other collider with a Z vertex as a descendant, that would contradict our choice of C. And then finally, this segment is active because it contains no X or W vertices, and it's just a chain. And this segment is active in H because it was active in the augmented graph, and and it contains no colliders. Sorry, because it contains no Z vertices. And sorry, it contains no colliders that are made active by only Z vertices. And so when we go from conditioning on X, Z, and W to just conditioning on X and W, we're not going to accidentally deactivate any of the colliders here because all of these are made active by something other than a Z vertex. If it was made active by a Z vertex, that would contradict this being the furthest right collider made active only by a Z, or made active by a Z vertex before X or W. Okay, that was kind of a mouthful, but the punchline is deseparations here, or these deseparations happen if and only if we have this sort of deseparation. The reason for going to this detail is that this I find to be a much more intuitive condition than this. Reasoning about these augmented graphs, I think, is much simpler than trying to understand what is going on here. Like, well, anyway, it's at least a little bit easier, I think. Not that either one is particularly intuitive. Anyway, so now that we've established this, we'll prove that the rule follows from this lemma. Okay, so again, we're going to let H be this graph where we've removed the parents of X and the children of Z. And now we're going to assume that this holds and now use that this holds. So we now know that Z hat is independent of Y given X, Z, and W in this augmentation of H with respect to Z. I claim that this also means that Z hat is independent of Y given X, Z, and W in the augmentation only with respect, or sorry, in the augmentation with respect to Z of the graph where we haven't removed the children of Z, right? So I'm replacing H here with the augmentation of the graph where we haven't removed the children out of Z. And the reason for this is once we're conditioning on Z, there's no way to get, so there are two types of paths from Z hat, right? There are Z hat paths that go into Z and then continue down. And these are blocked by conditioning on Z. And then this condition establishes that we've blocked the other paths that are that use Z as a collider. So once we know that these are blocked, we also get to conclude the stronger thing that these paths are blocked in the graph where we haven't removed all these children of Z. And now we just use this deseparation. So we write well, so I claim that replacing the do here with an X is equivalent if we're already working in the interventional distribution. So once I've intervened on X, then I can condition on X. I don't really want to prove this or spell it out, but take my word for it. So this first manipulation, I've just replaced the do here with conditioning, but I'm still working in the interventional distribution. So this isn't a substantive change. But now I'm going to replace this with an interventional graph expression. So here, I've now switched to working in the interventional, the augmented model, and doing Z in the original model is the same thing as observing that this augmented variable has the value Z, and then observing that Z has the value Z. The distribution, yeah, okay. And then now I have an expression with a Y, X, Z hat, Z, and W. And I want to get rid of this Z hat to get something back in the world without intervention variables. And so I'm going to use exactly this deseparation. Or sorry, not exactly this deseparation. I'm going to use this deseparation, right? Because the graph I'm working in is the graph where I've intervened on X. And sorry. So I skipped a step, which is if z hat's conditionally independent from y, given everything else, then I haven't changed anything when I set z hat equal to epsilon. At which point I now am back in the world where z hat, or where z acts freely, and this is a genuine unforced observation of z. And now this distribution is the same thing as sorry, no, that's visible. So yes, the deseparation was needed to reason about, or to argue that setting z hat to z is indistinguishable from setting z hat to epsilon, as long as I'm already observing the value of z, at which point, when I'm in the world where z hat's equal to epsilon, that just is the original causal model where I haven't, that's a statement that I can say about the original causal model where I don't even have these intervention variables. Is that relatively clear? Yes.
Do you mean p hat for the second last line and third last line?
Yeah, so sorry, what I previously I wrote p hat for this distribution, and when I've in the model where I've added augmented variables. So I do mean p hat, though I also think as long as it's clear that whenever I have an interventional, or whenever I have an intervention variable, I'm working in a model where I've added those. I don't think it's necessary to, like, there's only one logical p in the world. I should add a hat. I'm going to be lazy and not add hats everywhere and just freely manipulate these quantities. It should be clear from context which world I'm working in at what time. There was another question. Okay. So that is rule 2. Let's move on to rule 3, which is maybe the most powerful in the following sense. So what is rule 3? It says that it characterizes when you can not only replace an action with an observation, as in the previous one, but when you can drop an action entirely, right? So here I have y given do x, do z, and w, and here I've removed the do z entirely. And this, it has a very weird formulation that often throws people, because it requires deseparation in this weird graph where I not only remove parents of x, but I also remove parents of a subset of the z vertices. This apostrophe shouldn't be there, ignore that. Namely zw, which is the set of z vertices that are not ancestors of w in the graph where I've already intervened on x. So first of all, to parse this, I would recommend just ignoring the do x component everywhere because it's constant. And just thinking, this is saying that I can drop the action do z if z is deseparated from our effect in the world where I've removed all the parents of z, vertices that are not ancestors of w. It's still not, I still don't have a great intuition for it, but yeah. Okay, so the meat of the claim, or the meat of the theorem is going to be this lemma, which is also not super intuitive to state, but hopefully gives a little bit more intuition. So it says that if I have a trail that's active in the augmented graph post-intervention on X, but where I've done augmentations with Z, and this trail only uses edges from this graph, then it's also active in this graph. And the reason this is going to be useful is we'll show that, well, we'll see why this is useful after we've proven it, but let's just prove it. Okay, so we need to give more concise names for these graphs. So G1 is going to be the augmented graph where we've done the intervention on X and we've augmented with respect to Z. G2 is going to be this graph where we've cut, in addition to Z, all the edges into the Z vertices that are not ancestors of W. And let T be a trail that's active given X and W and that uses edges in G2 only. Okay, so the issue here is that I might use only edges from this graph, but the other edges that have been cut might somehow still deactivate my trail. And so the claim is going to be that as long as the trail is active in G1 and uses only the edges that are present here, the other edges you don't have to worry about. So why is this? Well, first of all the orientations of edges in G1 and G2 are the same. And the set of conditioning variables is the same. So all non-collider triples, anytime you have V1 to V2 to V3 and it's not a collider, or it's a collider where the condition descendant is an X or W, you're fine. That'll stay active in G2 because you haven't changed anything in G2 and the conditioning set's the same. And if your collider is made active by X or W, it's still going to be active because you haven't cut any of those edges. So the only remaining case is a collider triple where a collider triple where there exists a W as a descendant. Sorry, let me back up a second. So my claim was if this is anything other than a collider or a collider where V2 itself is an X or W, you're fine. The only case you have to worry about is a collider where you have some descendant in W, because that's the only situation in which cutting an edge here could break this and prevent this from being active. And right, X has no parents in either this graph or this graph. So X is not the reason that this is active in either case. And okay, so the next observation is that So let's actually just give a name to this. We'll call it W star. And so this is going to be a descendant of in G1 of V2 that is in W. So now our claim is that this path is also present in G1. And the reason is that no Z hat, no Z vertex can be on this path because we've only cut Z vertices that aren't ancestors of W. That's it. So this path remains, and we conclude that it's also active in this other graph. So that was a handful, but I've established this lemma, and now we're going to show that we can always find. We're now going to show that a D-separation that will hopefully be more intuitive, but this was an unfortunate but necessary lemma. So we want to now use this lemma to prove this result. So we're going to assume that we have Y D-separated, or sorry, we're going to now show that that this assumption here gives us that Z hat is D-separated from Y given X and W in H, where H is the augmented graph with respect to Z. Sorry, it's the augmented graph where we've intervened on X and then added the intervention variables for Z. So actually, I'm looking at the time. I think this would be less illuminating than talking about the ID algorithm. So all I want to say is that what we're going to end up showing is that this condition implies this separation, and this separation is actually something that is sort of comprehensible, right? Z hat being D-separated from Y given X and W means that doing an intervention is gives you no information about Y once you've already observed X and W in the graph where you've already intervened on X. And this is exactly what you can see how if you were able to show this, that would immediately imply this, that you can drop an intervention on Z. So the bulk of the work in proving this is just establishing that this condition is actually sufficient to get this D-separation. But again, I'm not sure how illuminating it will be. So I'm going to move on for the sake of time. Yeah. Anyway, so we've sort of proven the three rules of the Duke calculus, which now leads us to the Spitzer-Pearl ID algorithm, which again, we're not gonna have time to say all that much about. But let me restate the context for this. So the question is, what causal effects can be determined from observed variables only? And that's we use the notion of identifiability to frame this more precisely. And so we'll say that the causal effect of an intervention do X on a set of variables Y is identifiable from P in a DAG G if it's uniquely computable from the observed variables in any causal model that induces the graph. So you have only access to the distribution over observed variables and a DAG which induces or which comes from a causal model with those observed variables. And this DAG, sorry, there should be a in a DAG with bidirected edges. The question is, can you compute the interventional distribution from the observed variables and the graph? And so the Spitzer-Pearl algorithm, which again is not the only identification algorithm, in particular, there was a contemporaneous result by Wang and Valtorta that was essentially the same as this, so the algorithm looked very different. And there have been a lot of different algorithms since then. They have an algorithm, ID, which will do one of two things. If the interventional distribution for some given target variables to intervene on and effect variables to look at, if that's identifiable, it will return an expression for P of Y when you intervene on X. And if it's not identifiable, it will return a witness to non-identifiability. So a concrete proof that it's not identifiable in a form to be described in a minute. So sorry, just to be clear, the input here is the graph and X and Y, the description of the subsets. And then you get a symbolic expression that you could then evaluate given your data or given your distribution over the observables to come up with a concrete answer. Yes.
Thomas commented, this requires positivity. Okay. The distribution, right?
Yes, and we saw it already in the example before.
Yeah. Positivity came up a lot.
Yeah. Just to say what Frederick just said, this requires positivity.
I actually, just to make one comment, I think what you've got there, it doesn't, but what you had on the previous slide did. Because I think the expression holds.
Okay. Let me think about this offline to figure out exactly what I mean to say, but and every line of the algorithm is going to turn out to be an application of the rule of a rule from the do calculus. I'm not going to have time to describe it. I'm basically just going to flash the algorithm on the screen, convince you that it's not totally incomprehensible, and then talk about what it finds when it fails, when things are not identifiable, because I think that's interesting in its own right, and yeah, I think it's worth thinking of. So what does this algorithm do? It takes in the way it's written, it takes in some assignment to Y, some assignment to X, your observed distribution in your graph, and it just recursively does one of a couple different things. So if you somehow are in a case where you're no longer intervening on anything, well, then it's just the marginal distribution on on Y that you get by marginalizing out everything non-Y. If your vertex set contains stuff that are not in the ancestors of Y, then you just recurse where you've restricted things to just the ancestors of Y. If you have vertices W that are not in X and they're not in the ancestors of Y, you look at the set of vertices that are not in X and not in the ancestors of Y when you've done the intervention, and if this set is not 0, then you have to augment the set of intervention variables to include these. And this is, I think, maybe the most mysterious step, because somehow you're getting some assignment for W that you didn't provide to the algorithm. And it turns out it will later not matter. And that the resulting quantity will be independent of W, which, but it's nevertheless needed for the algorithm. So subsequent steps rely on this decomposition into C components, which I'll describe in a minute. And the details, again, are beyond the scope of the next 20 minutes. But it's hopefully not as scary as it was a minute ago. So let me go through 2 examples that illustrate what it does. So let's look at the following graph. For this graph, and the following question, like, can we identify the effect of X on Y1 and Y2? And then as a subsequent question, can we do the same thing where we've added an edge from W1 to W2? So it turns out in the former case, the answer is yes, this is identifiable. And we get back the following not super terrible expression, which I don't have time to derive, and I'm not sure I could derive it without spending a lot of time if I were trying to do it by hand. But let me just introduce to you some of the tools that are needed to be able to run this algorithm. So the most important concept, I think, that is used in this algorithm is the notion of a C component. And so this is a, sorry, just to define some terms, a semi-Markovian graph is a DAG with the addition of bidirected edges. And so a C component here is is a connected component with respect to bidirected edges. So if this is my graph, I have two C components. I have one that consists of, sorry, I have three C components. One that consists of these vertices, another one that's just this singleton, and another one that's this singleton. And it turns out all the difficulty comes when you have, you can decompose your identification problem into a problem for each C component separately. Right, so step 4 says when you remove X, does that break if it breaks the graph into multiple C components, then you can solve the problem independently on each of the C components and then combine those in the appropriate way. And yes.
We have these bidirected edges when we have one unobserved variable pointing to the two.
Mm-hmm.
But what do we do if we have one unobserved that points to 3 or 4? Do we have like a notion of a hyper edge here, or do we just say, you know, I'm just going to take and put in all, you know, dashed pairs amongst these 3?
So we're going to just put in all dashed pairs, and the claim is that by doing that, we have enough information to decide if the problem is identifiable or not, and that all the conditional independence relationships between observed variables that are needed to compute the expression if we run the ID algorithm and it is identifiable, that all of those conditional independence relationships are described by putting in all these pairs. And so that's sufficient, even though it's not, you're not accurately representing the way that these hidden variables talk to things. It's sufficient to be able to solve the question to use this pairwise representation. Okay, so
quickly?
yeah.
Could you go to the example you just had up, I think, on the previous slide? I was just wondering, like, so the estimate we're interested in here is the effect of X on both Y1 and Y2, right?
Mhm.
So in this graph, though, like the effect of X on Y2 seems a little bit cryptic to me. Like the graph suggests there's no effect, right? Or am I misreading that? Like from X, there's no forward direction path.
Yeah.
I was just wondering because it kind of struck me as a kind of peculiarity, but like X and Y1, that I see that makes perfect sense. But
Yeah, I agree. It's a kind of weird example. It's actually from the paper in which the ID algorithm is introduced, and he describes a realistic sounding setup that leads to this graph as to why you'd be interested in looking at the effect of X on Y2 when it doesn't seem like it would have any obvious effect, given that it, or
If there is a path through Y1,
Not to Y2.
W2, right?
W2, but that's a hidden, no, but it's not a path from X. So first of all, in the formula, you could see, you could move the summation over W2 and it doesn't, as you observed, it really doesn't matter, it kind of factors out. But I think the reason it's given the example is because it's going to show non-identifiability when you get the extra edge that was in red.
Oh, I see.
And that's kind of,
So it's kind of setting up a counter.
it's setting up the counter.
I see. Okay.
yeah. And I think the non-identifiability is more surprising given that Y2 doesn't seem that, you know, adding this additional edge, given that X2 or Y2 still is not on a direct causal path, it's more surprising that if you're looking for the effect with Y2, somehow things go wrong.
Just to add one other little comment here, which is that if you identify the effect of X on Y1 and Y2, then that also means you know the conditional effect of X on Y1 given Y2 in this example. So that's why Y2 is not totally irrelevant here, because we're identifying a joint distribution.
Yeah, so this algorithm is going to use a decomposition of your graph into C components. So this sort of decomposition where each component is has a spanning tree of just bidirected edges. And the counterexample object is going to involve a C forest, which is an even more elaborate thing. So what is a C forest? It's a C component that is also a forest with respect to visible edges. And Y-rooted C forest is one. It means that it's a forest where the roots of the forest are in the set Y. So if Y was, so this was Y1, this was, this example, this is Y2 and I had a bidirected edge here. Now I have two C components only. Sorry, so let me add one more bidirected edge. So now I have one C component and a graph that on the visible vertices is a forest with roots at Y1 and Y2. So this is a messy picture, but this is a Y-rooted C forest. We'll see why this is relevant in a second. So the obstruction to identifiability is this object called a hedge, which involves C forests as follows. So if I want to identify the effect of X on Y, then if I can find a hedge with respect, or if I can find a hedge with respect to X and Y, then I have a proof that it's not identifiable. And a hedge consists of two R-rooted C forests such that the smaller one doesn't contain any vertex from X, and the larger one does contain a vertex from F, from X. So here F prime is a small forest, F is a large forest. F prime does not contain anything in X, F does contain something in X, and F is obtained by adding stuff to F prime. And the root of this, of these C forests, the roots, the set of roots have to be ancestors of Y. So the picture is something, the abstract picture is something like this, and I'll then illustrate it with a concrete example, which will hopefully give you a flavor for why, or a little bit of a taste of why this is going to give unidentifiability. So you have your set Y. So you have this F prime, which is some sort of confounded component, C component with roots at the Y vertices, or at ancestors of Y, that's also okay. But all of these are confounded together. And so this is your F prime. And then your F is obtained by taking this forest and adding some more edges that somehow preserve the confounding. And so that you get one bigger C component. And now here you have to have an X vertex. So this is still, I think, very mysterious. Let me illustrate with an example. So this is not the most interesting example because it's not really that surprising that the effect of X on Y is not identifiable in this graph because there are a lot of bidirected edges floating around everywhere. Nevertheless, you can hopefully see a little bit of what this looks like. So here, what is the hedge that proves that the effect of X on Y cannot be identified? Well, the smaller forest is just going to be the vertex Y. So this is trivial. And the larger one is going to be all four of these vertices. So first thing to note, is this a Y-rooted C forest or an R-rooted C forest where R is some ancestor of Y? Yes. So we have a root here at Y and a single tree. And then the bidirected edges in red are a spanning tree on that same set of vertices. So how does this show non-identifiability? So first I'm going to expand out the bidirected edges to include to explicitly show the hidden variables. I'm going to drop this extra bidirected edge. And now I'm going to describe two models that generate the same observable statistics that nevertheless produce different results for the causal effect. And that is a proof that it's not identifiable. So what are the two models? So I need to specify how the U variables are distributed, and then I need to give functions computing all the other variables based on their parents and based on their parents. Yeah.
That's the binary question.
Yes.
In the middle, you can have the fraction description of the data that can allow you to get some information of the parameter. Even if it's not point identification, it could be
yeah.
So the way that you are looking for to show no identification, it seems to me that you can use the same type of process to look for all the potential distribution that can wash on data, and then get some kind of informativeness from the model, right? So it's not clear to me why you want to answer the question in a very binary answer is point identification or not. Instead of what are the information that I may have from the microbiome.
Yeah. So the question was like, why are we interested in the kind of dichotomy between being identifiable and getting a single answer, or like we give up and say there's nothing at all we can do? And the answer is often we're not interested, and often there are more precise things we can say, but this is like the totally non-parametric, no assumptions at all setting. And it's at the very least, I mean, well, you can imagine a setting in which you have no assumptions that allow you to say anything more concrete. And it's a good starting point. And yeah, I think it's often interesting to consider restricted settings, or to consider, bounds that you can get even in the absence of identifiability. Yeah, and this counterexample will in fact like be bad in the sense that it is a very contrived example where things are like, it's easy to make assumptions that would break this counterexample. And you'll see that right now. So what is this counterexample? So I'm writing two models here that generate the same induced graph, and they're almost the same. The only difference is how y is determined. So again, well, not again, for the first time. So the u variables, each of them are set uniformly either to 0 or 1. And then every other variable in model 1 at least is set to be the parity of all of its parents. And so by the parity, I mean the sum mod 2. So if u4 is 1, u3 is 1, and u1 0, then z is going to take 1 plus 1 plus 0 is 2, mod 2 is 0. And then x is going to take it on value equal to z plus u1 mod 2. And so if u1 was 0 and z is 0, then x is going to be 0 as well. So that's how we generate the data. And M2 is going to be the exact same thing, with the one difference that y is just set to the constant 0. So the first claim is that the probability that we see y equals 0 in model 1 is 1. So the observable statistics on all the other variables clearly are going to be the same in both models because they're set according to the same equations. And so the only thing we have to do to verify that these two models generate the same observables is verify that y is always equal to 0 in the observational distribution in model 1. So why is that? Well, let's look at the expression we use to compute y. So I'm just going to trace back using all these equations and expanding each thing out one at a time. So y is w plus u4, but w is x plus u3. X plus u3, and then x is z plus u1, and then z is u3 plus u4 plus u1. And you'll see that the expression here contains every u exactly twice. And so the parity mod 2 is going to be 0, or the sum mod 2 is going to be 0. So the observational distributions are exactly the same. Now, why are the interventional distributions different? Well, when we intervene on x in model 1, let's look at the resulting graph. So we remove the z to x edge, we remove the u1 to x edge, and we change the equations for x in both models. And what happens to y? Well, y in model 2 stays equal to 0 because the equation defining it hasn't changed. But in model 1, y is now set to w plus u4, which when we expand back out is equal to x plus u3 plus u4. And now no matter what value of x we choose, there's some probability that u3 and u4 have the have parity, or sorry, there's some probability that this expression is not equal to 0. And so the probability that y is equal to 1 in this model is greater than 0. And in particular, since in model 2, it's still equal to 0, we have different interventional distributions despite having exactly the same observational distributions. So this is a very contrived example. There are lots of ways we can modify it to make it less contrived. So we could make things positive by kind of just adding some independent, by having each variable basically only half the time listen to its predecessors and the other half of the time set its value independently. We can do things like that. As long as we have this, but the point is, this is the kind of minimal core example for this sort of thing. Like we have binary random variables, and we get that y is equal to 1 with probability greater than 0 here, but equal to 0 here. And so we've established unidentifiability. And whenever you have a hedge, right, you have two forests where the smaller forest doesn't contain any x vertices and the larger one does. And the same model, this counterexample generalizes to any hedge, because you do the exact same thing where the only difference is you set the equations in model 2 to be the constant 0, where at the boundary of the smaller forest. So, okay, I'm going way too fast to make this at all clear. The point is, you can set it up so that the target of your intervention has a probability of, the target of your intervention in one model is just a constant, and the target of your intervention in the other model is the parity of a bunch of stuff. And you can set it up so that the parities all coincide or all work together so that you get a constant value in both observational distributions, but then when you turn to interventions, you get a difference. And just finally, what does the non-identifiability proof look like for the earlier example? So in this case, the non-identifiability comes from the following pair of forests. So our smaller forest is W1, W2, Y2, Y1. So it doesn't contain X, and it is a Y-rooted C forest, right? It contains this vertex and then these two edges. So it's a forest and the roots are Y. And then it's a single C component because there's a bidirected edge between W and Y2, W1, W2, and W1 and Y1. And then the larger forest, just comes by adding back in X, and it's still a C component because of this edge. And then you can apply the same sort of counterexample to prove non-identifiability. And so here, it's important that we're looking at the effect on Y2 to get non-identifiability, right? If we were just looking at Y1, then this counterexample wouldn't work. Right, we couldn't find some, I think it wouldn't work.
You need to include, because the C component would need to go through W2 or Y2, and but then that wouldn't be part of a forest rooted at Y1.
Yeah, okay. Yeah, so what Leonard just said, right, we need a C component that goes through Y1 and eventually through X as well. And there's no way to get that without going around to this stuff over here. Yeah, anyway. Okay, I think I'm past my time, so that's pretty much all I wanted to say. Yeah.
Thank you. Are there questions? Maybe, well, maybe Spencer.
What was the algorithm, we went through it kind of fast.
Very fast.
It had this recursive step.
Mhm.
What is the running time of this algorithm? Is this thing that like just terminates in a finite amount of time, or does it have like a clean running time? Is it?
I don't know, and it's a little bit hard to say because it depends on whether you treat it symbolically or numerically, because the input, if you think of the input as just being a graph and not like a concrete distribution, you can get some symbolic expression in, I think, linear time, but then because the recursion recurses on strictly smaller graphs, and I think on disjoint portions of the graph, as far as I remember. So I think it's linear time symbolically.
So the same question was asked on Zoom actually, and Ilya is on Zoom, and so he gave an answer that says it's two-part really of answer to the running time question. One is, do you look at this algorithm just as answering the question of identifiability versus non-identifiability? If that's just all you're doing, then it's apparently no polynomial. If you are also asking about getting the actual estimator for it, so when it's identifiable, you want to get the actual estimator. It's much more complicated. But
when you say estimators here, do you mean the expression itself, or what do you mean?
Yeah, the functional to actually compute probability of y given do x. Like
Okay.
But which let's just say, if for that second question, the input size is quite different. So for the identifiability question, your input is the graph and the set X and the set Y. For the second question, you need the distribution, which is exponentially larger. Suppose these are binary variables, just so then the input is exponentially larger, actually.
But except it factorizes, so it depends a little, right?
There is a concise representation for it after the fact, but as an input, as a raw input.
But statistically, we take the input to be data, so
yes,
it might be
supposed
smaller.
to be positive data. It's supposed to have.
No, not necessarily, but anyway, yeah.
Thomas, do you want to go with your question?
Yeah, so I just had a comment which is just a notational comment, and it may be clear to everyone, but it was something which struck me about the notation from this morning and from the results that were being presented this afternoon. So essentially the point is that may be obvious to everyone, but might not be, is that the notation P sub X, which you are also using to represent do of X, that is a function of a graph that you are positing. And it's not just a function of the distribution. And so in particular, you had the results this morning where you said I could have two different graphs that are Markov equivalent. And those two, if two graphs Markov equivalent, then a distribution that is Markov or compatible with one graph will be compatible with the other graph. And then this afternoon, you had a result that said, well, if a distribution is compatible with a graph, then the intervention distribution P sub X will be compatible with the graph G sub X. And because P sub X and do of X aren't indexed by graphs, somebody might naively think that then, okay, well, if G and G star are Markov equivalent, then P sub X is the same from both of those graphs. And so I just think it's important to stress here that that's not the case, that whenever you talk about P sub X, there is a graph in the background, and the P sub X you get out from a Markov equivalent graph will be different even for the same distribution. That was just a comment, and maybe it's clear to everyone, but I wanted to emphasize that because the notation kind of didn't show that.
That's all the questions I saw. Are there any more in the room? Let's thank Spencer. Okay, the section outside. Tomorrow we'll be talking about causal discovery. Dan Malinsky will be doing the presentation. So today we saw a lot of results that assumes knowledge of the graph. So tomorrow the question will be, how do we get the graph in the first place? Right? So back here at I think it's 9:30 again. So if I have that right, hope to see you then. Enjoy the reception. Thanks.